My name is I'm majoring in computer science.
And I'm Steven Linares, and I'm majoring in cybersecurity.
We are here on behalf of our Team 5 Computer Science from Union College, Agribusiness Internship. Together we worked on an embedded IoT monitoring system for real-time hydroponic environmental monitoring. This is the rest of our team, Liz Dishvali and Joshua Jensen, who are both computer science majors and conducting it today. Our goal was to create, to design and implement an IoT monitoring system that would monitor the hydroponic systems in real time, collect environmental and water quality data, transmit that data wirelessly, store the historical measurements, display them live on a dashboard in real time, and support future greenhouse automation. That led us into a research question, since we knew what our goal was. Can affordable sensors and ESP32, a Raspberry Pi, and open source software be combined into a system that continuously collects, transmits, stores, and displays live and historical hydroponic environmental data? So our first question, our first step was figuring out what we needed to collect. What kind of data was useful to collect from our hydroponic systems? What was useful, what wasn't? We decided that we needed to measure the temperature, measure the electrical conductivity. We needed to know the water level, so we would know when it had to be refilled. We needed the data from the greenhouses themselves to know the humidity and the temperature. We needed another water sensor for our components to make sure that no water got on them. So if it did get water on them, we would know, and it would shut off so that our system wouldn't get messed up. And the last thing was our pH sensor to measure the pH.
So before we begin, I'd just like to give a huge thank you to Taylor Lopes for having a background in biology. With her help, we got the measurements needed. And with Dr. Mohammed, with his knowledge on hydroponics, we figured out how to implement these sensors. Right. So we're going to start off with the ESP32. Right. We chose an ESP32 because of 6 key features. It has Wi-Fi capabilities, it's easy to program, it's reliable, it's beginner friendly, it has low energy consumption, and it is compact. It is the size of your palm. With that ESP32, we connected it to a microcontroller, or a microcomputer called a Raspberry Pi. It is the same thing as that laptop here, this computer here, but smaller, also the size of your hand. Right? It is being held inside Dr. Mohammed's office for safety. Right? The way we send data is called a protocol called MQTT, which stands for Message Queuing Telemetry Transport. Right? We use MQTT because it has low bandwidth and it is perfect for inconsistent Wi-Fi or weak signals like in ESP32. So, the way all this works is one big flow. Inside the Raspberry Pi, we're hosting something called an MQT broker. Basically, it opens up a port inside the Raspberry Pi so that it can allow communication. That communication is then being processed by something called Node Bergen. It takes the raw data that's being sent by an ESP32 and then it breaks it down into a JSON file so that it can store the data inside something called Influx. It is a locally hosted database. And then from that database, we use something called Grafana, which basically is a dashboard application. It takes all the data from Influx and the timestamps of when the message was sent so that it can broadcast the sensor data inside Grafana. So here's a complete project workflow. If you guys are interested, you guys can take a photo at this moment. This basically brings all of our data together into one panel so that you guys can see.
So workflow looks very organized, but actually working on it wasn't that simple and as organized. Here is when we were setting up behind our the hydroponic systems. And this is when we were installing Linux in a Raspberry Pi. So this is how small a Raspberry Pi is. And here, this is our server. So this is what handles pretty much everything. So we faced different types of challenges throughout our project. So we had technical challenges, which were learning Linux, learning MQTT, Node-RED, Influx database, and Grafana. We also had to work with our IT department to set up our system with the WPA2 Enterprise Wi-Fi, which is very different from your home Wi-Fi. We had to calibrate the sensors, which was also not easy and took a lot of redoing until we finally had reliable data that we were getting. Also, hardware wiring was not simple because we had to do it right behind the hydroponic system. We could not tamper with the hydroponic system, so we had to figure out a way to get our sensors inside the water, through the back, and then we had to solder them on right there in the spot, and we did not have a lot of space to do that. We also dealt with environmental challenges. We dealt with water leaks, and moving the hydroponics units was one of the things that caused that when we had to get behind it and work on it. We dealt with high reservoir water temperatures, and our reliability challenges were power outages. So we dealt with a couple of power outages with the rain and the storms. And then we also had to worry about waterproofing and sensor placement. As I said, it was pretty difficult because we could not tamper with the hydroponic system at all. We had to get it done with whatever we had. So we didn't just work on the computer science side. First of all, we had to work on greenhouse maintenance. And this is where our work began. We had to measure pH, we had to check water levels, we added nutrients, clean hydroponic system, we repaired leaks, we monitored plant health, we recorded observations, and we harvested crops. And all of these things that we did is what helped us figure out what we needed for our sensors. So these are some of the crops that we grew. We grew carrots, lettuce, cucumbers, watermelon, spinach, bell peppers, and bok choy. Here's some pictures of them. So I'm not going to go into deep with the plant development, but here's information of the things we did grow, that did germinate, that we did harvest. Some of the plants did not germinate, and we replaced them with other plants, and we just kept going until then. We're still going.
So as for our results, we worked within the span of 2 months. We worked with ESP32 firmware. We successfully integrated sensors into the hydroponic systems. We established wireless MQTT communication. We designed Node-RED automation, and then all of that being fed into a database, right, using Influx. And we had live Grafana dashboards, which will be shown right now.
So this is what I have access to monitor our plants and our hydroponic systems. This is the friendly user interface, because obviously I don't understand all this stuff. I'm a bio major. So as we can see here, we could monitor the humidity, the pH of the water, how full the reservoir is, as well as the inside temperature of our greenhouse and the outside, because we have 2 greenhouses. And all of this is just monitored through here, super easy to use. So this is very useful for someone like me.
That dashboard is live. It refreshes every 5 seconds. And because we are in the computer science team, we have access to it wirelessly from wherever in the world. For normal people who are not in the computer science team, they do have to be connected to the wireless Wi-Fi there. So we couldn't bring the QR code for you guys to scan your phone. Here's some of our photos of us working together. You can see all the cables on the right side. It's a mess. And it's still a mess. We have to clean it up when we get home. But it was really fun working on this. So, this is what we just showed was the dashboard. For general greenhouse usages, we have 2 greenhouses, an inside and an outside greenhouse, right? So, as you can see with my pointer, these 2 are for the inside greenhouse. We measure humidity and the air temperature, right? So at the day when I took this photo, it was 93 degrees Fahrenheit. And in the outside greenhouse, it was also 93. It was cloudy. during the time and it rained, so the humidity is at 50%. For our specific hydroponic system, we have these 5. This is the water temperature sensor, which was at a staggering 92 degrees. There was enough water in the tank. There was sufficient water injected. Because the ESP32 is not waterproof, we had to put it in a separate box. This measures if there's water inside the box, and if there is, it sends us an alert because it could ruin our entire system. This is the electrical conductivity sensor. Basically, its main purpose is to tell you how many nutrients are in there. Because if you put metals inside water, it becomes more conductive. So it measures that using a unit that's more readable for humans. And then our final sensor, which is just the pH sensor. The way we calibrated the pH sensor was we had to read the raw voltage output every time we put it inside the buffer. So like the 4, the 7, and the 10, like normal, right? We had to read it and manually write the equation for it. For sure.
So our internship was agribusiness, not just agriculture, right? So we had to find the financial side, like how does it benefit us financially? So our system is very affordable compared to commercial monitoring systems. Also, you can make it yourself. So everything that we use, you can do it yourself. The continuous monitoring reduces risk of equipment problems, which cost you money, leaks, low water, high temperatures, unnecessary manual checks, and fix small problems before they become big ones. So it really helps with not losing plants. And then it starts historical data. So you can go back and you can see what happened last week. Why did we lose this plant? What changed and what was wrong? What can we fix for next time so that we do not lose that crop? Because that's also losing money. So we have ideas for future improvements that we unfortunately didn't have enough time to implement during our internship. So alerts, so that interns get alerted. Automatic misting for greenhouses because they get really hot throughout the summer. Battery backup since we did have power outages. Generator integration for the same reason. And AI plant monitoring using cameras and automatic nutrient dosing and a water cooling system since our water did get really hot in the reservoirs in the units. So for acknowledgements, we would like to thank Just Pathway UCNJ for the internship opportunity, Hector in IT, who helped us a lot connecting to the Wi-Fi, Dr. Alexander Rubos for technical guidance and the initial implementation of our water level sensor and continuous support.
We'd like to thank UCNJ's Innovation Center for hosting our equipment and lending us a workspace. We'd like to thank Professor Ebert, Remy Warfield, and Agribusiness Engineering Team 1, which are these two right there, for designing our mounts for the 3D printed float switch and our other sensor mounts. Because the float switch, the way it works, it must stay vertical. And then an individual thank you to Taylor Lopes for her plant knowledge and her hydroponics expertise.
And we would like to thank our mentors, Dr. Mohammed and Dr. Donovan Smalls, for the continuous guidance and support throughout all of this. Another thing I'd like to add, they did mention about our project being used on theirs. It can be used on any hydroponic unit. So it doesn't matter on any unit, but we were thinking especially for theirs so people want to monitor it. But this is something that people can do themselves.
Any questions?
So where are you going after this? What's next?
Straight to work, actually. Me personally, I feel like my certifications can lead me to a job instead of having to go through a bachelor's. And even then, I'd say a company would allow me to go back to college while working.
And also, you mentioned to me thoughts of like sharing the code you use for this to even happen. What are you going to do with that?
The code, we basically...
We have to create another repository because our private one has our private